Hi everyone, I'm Nilanjan from India. I'm a postdoc at the Center for Condensed Matter Theory, Department of Physics at the Indian Institute of Science. So the title of my poster is Single Particle Excitations and Fock-space Propagator across non-ergodic extended to ergodic state phase transition and many-body localization proximity effect. So this work is done with Jagannath Sutradhar and Sumilan Banerjee at IISc Bangalore. So the questions we are addressing here are actually whether there is a new diagnostic to investigate the MBL proximity effect. So the MBL proximity effect, as you know, is that if we keep an interacting localized system in contact with a thermal bath, then the relevant question is whether the thermal bath gets localized under the influence of the localized system, or whether the localized system gets delocalized under the influence of the thermal bath. So when the first case happens, that the thermal bath gets localized under the influence of the localized system, then that phenomenon is known as MBL proximity effect. So in our case, we consider generalized Aubrey-Andre-Harper model, which has a single particle mobility edge. So here, the delocalized states actually plays the role of the thermal bath, and the interacting version of this model has been reported to host ergodic states, non-ergodic extended states, and also MBL states in the many-body spectrum. So we will try to demonstrate this MBL proximity effect in such a system through a new diagnostic. And next question is how different this non-ergodic extended phase from the MBL or ergodic phases. Can one address this difference again through a new diagnostic? And then can one also characterize the non-ergodic extended to ergodic phase transition, or MBL to non-ergodic extended phase transition? So we actually find diagnostics which are based on single particle excitations in real space and Fock-space. So let me skim through my presentation. So this is the model, which is the generalized Aubrey-Andre-Harper model. So there is a quasi-periodic potential, and in the non-interacting limit, this model contains a very sharply defined mobility edge, and in the interacting version of this model has been reported to host all three states, as I have addressed already. So here we actually consider the single particle excitation in the real space, and we calculate local density of state, and through this quantity we demonstrate the MBL proximity effect in this system. And in the Fock-space, we actually look at the Fock-space propagator, and more specifically, we look at the local and non-local propagators. The local propagators gives you the Finberg self-energy. So we studied Finberg self-energy to detect the ergodic to non-ergodic phase transition in the Fock-space. And also one can study the distribution of the same quantity to get more information. And then we look at the non-local propagators, and from the decay of the non-local propagators, one can define localization length. That helps us to detect the MBL to non-ergodic extended phase transition in the Fock-space. So here is our conclusion. So we look at, we demonstrate MBL proximity effect through the typical value of local density of state in the real space. And we find that the single particle excitations are delocalized for ergodic phase and localized for MBL phase. But surprisingly, we find a single particle mobility edge, even in the presence of interaction separating the localized and delocalized excitations. And we look at Finberg self-energy to detect the non-ergodic to ergodic phase transition in the Fock-space. And also we conclude that MBL and non-ergodic extended states both are multifractal in the Fock-space. And from the non-local propagator, we calculate a Fock-space localization length that helps us to detect or distinguish MBL states from the non-ergodic extended states. So please stop by my poster if you're interested, and thanks for your attention.